Good afternoon, my name is Corey Cohen and I'm here today to talk about design pattern recovery from malware binaries. So I wanted to begin by just kind of framing the problem domain that we're working in. We're talking about automated binary executable static analysis. And it's got a number of applications. It can be applied to software assurance and answering basic questions about the functionality of the code. Do we know what it does? Does the binary do what we think it does, etc. But my background is in malware analysis, and I like to think of the problems in terms of how we can apply binary executable analysis to malware problems. The problem that the DoD faces with malware analysis is that it's very time-consuming, it's very complex, it's very manual. The process requires a very specialized skill set. It's hard to hire for, it's hard to train for, it's hard to staff for. And we're looking for ways to leverage the existing knowledge that we have, to leverage experience developed by senior analysts so that more junior analysts can learn from that, and then ultimately to automate as much of that process as possible. So of course, in order to do this, we need a solid foundation, and there's a whole bunch of things that we have to have in order to be able to build such a platform. One of the things is we need a file format parser. We need to be able to read PE executables. We need a disassembler that will take the binary bytes in the executable and turn them into assembly instructions. We need a function partitioner that will take those instructions and decide both where to find instructions in the binary and how to group those instructions into functions, which turns out to be a relatively challenging task. We need a set of instruction semantics that explains what those instructions do. We need an emulation framework that allows us to step over those instructions and emulate them in an abstract domain and talk about the behavior of the program. We need to be able to do things like compute usage and definition chains. We need to integrate with an SMT solver to answer questions about reachability and expression equivalence. We need algebraic simplifiers, etc. So there's a whole lot of pieces that have to come together to build one of these frameworks. And we looked around a little bit and we found the ROSE platform. It's a compiler platform primarily, source-to-source transformation. But we've been working very closely with LNL for a number of years on the ROSE platform. It's open sourced, it's BSD licensed. It's a C++ library, it's highly extensible, and we've been extending it. And what we've been extending it with is things like calling convention detection and stack delta analysis. It allows us to track the value of the stack pointer as we evaluate the program. We've been adding parameter tracking and interprocedural parameter passing, and this year we worked some on type recovery as well. So as you can see, there's a lot of pieces that have got to come together. We've used ROSE for that framework. A couple of years ago, we had a research project to do object-oriented analysis recovery. That tool is called OBJDigger. And I'm going to tell you a little bit about it because it's relevant to this year's work. The idea was to take binary executables and recover the high-level abstractions that are represented by C++ source code concepts. The assembly example there has many little details in it that if you know how to interpret what the compiler does, you can say, oh, this must be a constructor because it's the first function that was called, and this must be a vtable because it was initialized in a particular way. And our goal in OBJDigger was to take those very low-level facts that we found in the binary, accumulate that data, analyze it, and reach conclusions about the higher-level abstractions like, oh, there must be a class, and this class must have these methods associated with it, and this class must have these members. And there's a relationship between these two classes. One is the parent of the other, and so on. And so we built that system a couple of years ago, and we've been using it in malware analysis, and we've been enhancing it as we went. And it's going to serve as one of the data sources for this year's design pattern work. So the problem that we're facing in, quote, the design pattern recovery problem is that malware authors face the same challenges that legitimate software developers do. They want to develop reusable components. They have goals like exfiltrating data and being evasive. And they want to be able to reuse those components. They want to be able to software engineer those components in the most efficient, most effective way. A lot of this is driven by antivirus methods that are attempting to detect them And so they're constantly needing to permute and churn and change these components to avoid detection, but they don't want to have to keep rewriting them from scratch over and over and over again. So as good guys, as malware analysts, what we want to do in those situations is we want to recognize those higher abstractions in the binary. We don't want to talk about individual functions and individual instructions. We want to talk about, a command pattern or a command dispatch loop or other things that are higher level constructs. And there's anecdotal evidence that those kinds of patterns exist in malware. So this slide, I'm not going to dwell on long. It's a source code implementation of the command pattern that was represented as a graphic on the previous slide. And as you can see here, we've picked up a whole bunch of additional features and a lot of detail, some of which won't be available in the binary, such as public and private, method names, relationships between classes, etc. But this is the first stage of the transformation. And then we come across something like this, which is the binary implementations of the constructor and the exec method from the previous source code. So it's just a small piece of the source code that was on the slide before. And obviously many of those source code features have been obscured. But there are still things that are there. We can key on these things. We can find, as I mentioned earlier in OBJ Digger, there's a reference to a VF table there. Many of these features are required for execution, so they have to be present. We can identify the calling conventions of the functions, and we can enumerate all of these features, much like we did with OBJ Digger, only this time for recognizing the command pattern. So our approach here was to enumerate all of these little individual binary features that we believe describe that particular pattern. So we might say, okay, there are 4 classes, and one of the classes inherits from one of the other classes. There's a constructor for that second class that takes a particular type of parameter. There's a method on that class that calls some other method that we can identify as part of the relationships. We might say one of those methods is virtual. We might say that one class contains an instance of another class. These are abstract properties of the malware. They're not individual instructions and individual byte sequences and things that are syntactic. And so our approach was to enumerate these features, describe their relationships to each other, and test for the existence of such a pattern. So what we actually did in our prototype was we decided to express the facts that came out of various tools that we have built, and I'll talk about those more in a demo tomorrow, but we took those facts and we exported them as Prolog facts. And then we took the pattern that we were looking for, and that was expressed very naturally as a set of Prolog rules. We just make assertions about what kinds of abstractions we see in the program. And then we invoke Prolog, and Prolog will help us figure out whether those facts match that pattern. We conducted an experiment by compiling a malware family example. We built it from source. It was a ghost or an evilite variant. We detected in that sample a variety of classes and methods and functions, and we did it using the class relationships and the API sequences and components of the call graph. The core pattern that we detected was a socket class that handled the I/O communications of the malware, and another class that was essentially a generic command class. And those two classes had pointers to each other and invoked certain methods on each other in a way that was highly predictable. And then for that generic command pattern class, it had subclasses that implemented specific things like a keyboard capture command, or a screen capture command, or a remote shell command. And by identifying the parent-child relationship between those individual command classes, we were able to identify a bunch of attributes or abstractions in the malware. We were also able to use this approach to find a number of procedural functions that would do things like dispatch commands as they came in over the socket. So we still have more work to do. We need to continue to improve the accuracy and completeness of the features that we use to reach these conclusions. We need to conduct some more experiments on pattern variation in malware. Our belief is that the abstractions that we're currently working at are going to be high enough to detect in multiple variations of the same family of malware, but we need to conduct some real experiments to prove that. We need to continue to explore whether or not the expressiveness of the features we've chosen are sufficient. Based on our experiments thus far, they seem to be. And then, of course, we need to implement some new feature exporters as well. So we've detected numerous examples or functions in a malware sample. And the reason why this is of benefit to the DoD is because when a malware analyst has done the work to identify these features once in a particular malware instance, they can codify these observations into a pattern, and then other instances of that malware file that they encounter, they can run this tool against it, and the analysis that they did about figuring out which functions were which and which classes were which and what to name the methods and all of that kind of stuff can easily be transferred from the one file to another. And of course, this is going to reduce effort and it's going to improve. I could be an experienced analyst that would make that pattern, and then I could give it to a more junior analyst who could use that pattern to understand a piece of malware they hadn't previously encountered. Finally, we're going to focus on deep compilation to source code in the coming year, and our goal there is primarily to allow source code tools to be used in the analysis of malware binaries.